I will first cover the part one and part of the part two, and then I will switch to Yusu to cover the important demo to show you how it actually works. And then actually Mariana will also talk about, before that we'll talk about the some of the important part is how we integrate the AI-based work with existing tools to come to a more complete solutions. So that's an important piece and distinguish many of the existing work, because most of them, they are probably just talk about AI and in a simulation environment, but haven't touched on the integration with other part of the system. So this is the important part, and Mariana will share some details and how we are able to make it. And then after this concrete examples from API project, we will discuss a little bit about other recent progress in AI for grid operations and give some perspective about the future work. Yusu, could you go to the next slide? Yeah, I think here just using two figures to show that the future grid will be very different from what we have today, and it will be even, as you see on the right hand side, our predictions usually failed in a way that we are more conservative in our prediction. So it could be, I mean, the future will be coming even sooner than what we expected. So this require very different operations scenarios and techniques to support the future grid. Next slide. And here just showing that we are already facing many challenges, and this challenge will be even more significant as we moving into the future with faster dynamics and very different fast changing operation conditions. So this is as you see here are two examples showing that there are many events happening in a very short time, and these operators are very challenging to control them. And the one on the left hand side is from the 2011 Southwest blackout in US. As you see, many consecutive events happening within shorter than 5 minutes. So which means that operators, if they should respond in a shorter than 5 seconds intervals in order to control them to prevent further propagations. And similar things like within 10 minutes, we have multiple events happening in the Texas event. Next. Oh, I can control this slide. Okay, great. Sorry, maybe there's some delay, so I will get used to it. And here is basically to summarize the challenges of achieving emergency control such that the operators can mitigate those events even with increasing uncertainties. So this is the requirements in terms of, oh, sorry. User, could you take back the control? I don't know why it keep moving forward. Basically, it's the requirement in terms of scalability, solution time, and security and adaptabilities. So we see that this is the much stronger requirement compared to many other applications of AI in other domains because of the scaled system as well as the security requirements as well as the solution time. While at the same time, we look at the existing control method in power system, we see, for example, industry, mostly they're using these rule-based control. We are talking here about some of the wire area control or system level control. So these are rule-based, and they are not adapted and time-consuming to develop and update. And in terms of research, we have seen model predictive control and learning-based and or data-driven control for quite a while, but they still suffer from the scalability and solution time or security kind of issues. So our questions to ask, actually, Yusuf, could you go to the next slide? Is that we see AI has been achieved good progress or even some very good success in, for example, in games. As you see highlighted here, like Go and OpenAI, how can we bring such a success to controlling or operating the complex system? This is a huge gap, right? And what we are going to show you today is some of our early work to basically try to approach to the from the left-hand side to the right-hand side. So we will show you the journey that we walk through. Next. And here, the common thing that behind, for example, the success of AlphaGo and the OpenAI games is these deep reinforcement learning. This technique is designed for solving sequential decision-making problems. So it's by nature fit into the grid control quite well. And how this works, basically, as you can see from the figure here, the agents was able to learn the control policies through interacting with the environment. And this process through trial and error and guided by the reward signal, which is on the right-hand side of these figures. And through this kind of trial and error, you can expect it could take a lot of time in order to come up with a good solution. And then if the agent is represented by the neural network, it's very hard to impose some hard constraints. So these are the challenges, and we will go in more details when we talk about how we apply this to power system and how we improve it. And deep reinforcement learning is the latest development in this domain by incorporating not just neural network, but a lot of development of deep learning techniques into the reinforcement learning. And as we also see that IR-based control and operation of power system is not new. It has been here for at least 2 decades. So the previous work showed the promising results, but the thing is that they are more focused on the small scale studies like IEEE 14 or 39 bus system. While here, our work is more focused on how we push the boundary to a larger scale system like 2,000 or 20,000. Next slide. And here is the key challenges that we have to basically push in order to achieve applicable to solutions for large-scale power system control in terms of scalability. We are talking about, for example, using an example of the Western interconnection of the United States as an example about the scalability we need to adjust, and safety and adaptability to the changing operation condition, as I showed before. So these are the 3 main challenges that we have been considered. Definitely, there are other challenges. Next. And if we want to adjust these challenges, I think one important things we observe, and also other industry has been goes through, is that not just breakthrough in AI, but also we need to leverage other advancements to adjust those boundaries. And one thing is clear is that not only the development of AI solutions or AI algorithms, is the advanced computing is also an important part of the solution. And how to leverage that will be critical factors to whether the solution is scalable or applicable to large-scale system. And if we look at I had quoted as kind of a statement from or lesson learned from Professor Rich Sutton, who could be regarded as the father of reinforcement learning. He said that the biggest lesson that can be read from the 70 years of AI research is these general methods that leverage computing are ultimately the most effective and by a large margin. So this we also follow these directions and by developing our solutions. Next slide. And another part of AI, I think, particularly for power system, is physics. Because of a power system, we have gained more than 100 years of knowledge and physics understanding and modeling. This cannot be dropped. And actually, most of the AI application and power system can fall into the area with small or medium size of data, while we have good amount of physics and knowledges. And how we're able to leverage both the AI and physics will be an important part in the solutions. And we see existing works has been already showed good and promising results by embedding physics into AI, for example, by leveraging our understanding to create observational bias or inductive bias or learning bias. These are good and practical ways to improve the AI by incorporating physics. And we also share our solutions in these directions. Next slide. So to sum up, I think our final research framework is like this. It's achieving the convergence of physics, AI, computing, and control for decisions and making at large scale. And the key observation from our research is that there are strong connections among them. And as for example, when we are working on these reinforcement learning-based control, we already have a lot of understanding of existing physics-based control and how we embed those principles and objectives into that learning-based control is an important part in our research. So by leveraging this kind of connections is important way to overcome some key challenges in each of those domains. And another part is that, as I highlighted before, many recent breakthroughs are actually achieved through this kind of similar convergence. For example, AlphaGo, AlphaStar, or the recent breakthrough like AlphaFold. Those are highly integrated about AI, physics, or the underlying of the chemistry, and leveraging computing and simulations. So we believe such kind of convergence is a way of the future. Next. So I give you the background. Now I will start to give a little bit more detailed background through this or technologies through this concrete example, which is our API Hedgehog projects. So this project is aiming to go to the next slide. So this project is going to, the objective is to construct intelligent and real-time emergency control decision support tools to provide effective and fast control actions to the operators. As you see, existing practice, basically operators are in the driving seat and they are under significant both momentum and decision-making burdens. So our solution is basically able to, is to come up with and develop AI-based decision support tools such that these humans can become a supervisor of AI instead of in the driving seat of the whole decision-making process in order to make the decision more efficient and fast, much faster than the existing practice. And this is a team effort through these 4 organizations. Next. And as I highlighted before, we are targeting large-scale power systems, and this is basically our technology roadmap. That in the second year we scaled up to handling a synthetic 2,000 bus Texas system, and in the current year we have been working on these 20,000 buses for the Western interconnection of the United States. And there are 3 different control schemes we have considered, including the under voltage load setting for voltage control, generation shipping, and control islanding. Next. And here is more details how we actually address these challenges and by using AI, physics, advanced computing, and control. So these is solutions. Each of these are able to basically combine together. So I highlighted this algorithm for each challenges, but this algorithm is like working like a Lego. So they can be combined, and which has been able to achieve the final demo that we're going to show. Here, I would like to highlight, for example, for the scalabilities, we found that existing DRL algorithms are not able to scale very well to the scale we are talking about here. So we developed these parallel augmented random search algorithms and marry it with these high-performance simulation platform group pack developed at PNNL. And on top of it, we using, for example, smart sampling techniques for scenario reductions. So all these combined together are able to help us adjust these scalability challenges for large-scale power systems. And in terms of safety, as you see, one of the things is incorporating physics into these DRL agents, and we have developed techniques for trainable action mask, which we will give you more details in the next few slides. borrow some ideas from the control community. For example, these control barrier functions to further enhance these the securities and safety of these agents. And in terms of addressing these fast changing operation conditions, we have been borrowed the idea of meta learning, and particularly is the concept of context, like human behave adaptively through different contexts of the environment. So we basically train these IO agents to learn the context by themselves and fastly adapt it to the new operating condition by training that context. So these are the main ideas that we have been come up with to address these challenges. Next slide. And this is the highlight the overall platforms that we developed in order to achieve these progress. And part of it on at the bottom is the two modules. One of these learning module and one is the execution module. So the learning module, I think, is the most important in terms of training a good AI algorithms for large-scale power systems. And and figure 2 basically is a high-level architect of this solution by able to scaling from laptop to all the way to HPC cluster and cloud. And this is due to we develop our solution being compatible with Ray infrastructure, which is a highly it's open source and highly scalable toolkit or platform for such kind of applications. And in terms of execution, once we trained this neural network or neural network-based IO agents, then we will basically move on to this real-time operation mode. And this decision-making module will be in the loop of the decision, and we could further leverage GridPack for further faster than real-time validations if needed by the operators. This is something, a unique solution that we can verify these AI decision makings in the loop. Next. And this is more detailed about the algorithms. So the basic, so here is showing the base idea of these augmented random search. So I think for those aware of optimization or control is that once we know the gradients of respective to a control objective, then we can easily update this the searching or our neural network by using this gradient. And here we are not using, for example, those AD or back propagations. We're using this kind of random search that to basically to using search around this current operating point in the neural network space to find out what would be the good directions as for the neural network update. And here, as you can see, it has inherent parallelisms because of each of these directions is independent from each other. But we can also leverage the information from the previous search to guide it these gradients search. So this is actually how we use at the end. And as you see from the right hand side, all this process could be achieved in a two-level parallelizations in terms of both these worker level, which is basically the worker in terms of executing this search. And we can also parallel these environments such that each workers can interact with multiple environments for this searching. So these two levels parallelization are able to achieve very good results. I will show you in the next few slides for some studies. Next. And this is the how we incorporate physics into this DMRL. And the key idea as is showed on the left-hand side in the figure, as you see, power systems have a lot of knowledge in terms of standard and performance requirements. For example, this voltage curve. And here, we basically embed these requirements using this action mask to modulate or regulate the output of the neural network. And this is can be regarded as the fixed action mask. But we know the system is changing, and a fixed action mask or a fixed requirement may not work for different seasons or even different days in a week. So we further improve this by making this mask trainable such that it can be adapted to different operation conditions as well. And this is how we actually develop at the end to train both this action mask and a neural network at the same time. Next. So this is talk about how we leverage this deep meta reinforcement learning for addressing the adaptability issue. So if without this meta learning, the DRL solution basically is you develop one policy to adjust many different power flow based cases, very different dynamic models and configurations. So this could be regarded as a one size fits all solution. Given that the grid is so complex as there's so many scenarios, it's very challenging to train such a policy and achieve good solution among all these different cases. And at the same time, we know that humans behave adaptively based on the context, right? The context is a very vague concept. And how we help these agents to learn a context would be important if we want to bring that context to these DRL agents, right? And to help adapt to different, basically different operating conditions. And because of even human operators don't know exactly like which part they should monitor and what should be, for example, if the group keep evolving, what would be the minimized information they would need in order to make their decisions. So this is a very complex, it's not that intuitive solution. It's very hard to hard engineer this kind of a context. So what we did is basically is to derive this two-loop learning process, as you see at the figure at the bottom. This two-loop is we have the normal loop for the normal DRL learning, but at the same time we have this meta-learning loop on the outside, and this meta-learning loop is basically to learn a low dimension. Basically low dimensions latent context by observing what has been learned in the past when we interacted with different scenarios and using this to maximize this performance under different operation conditions. So this learning context could be, is because it's a low dimension, it can be quickly adapt during this adaptation stage. And next I will show you more about this. Could you go to the next? Yeah, so this is basically the process, how we leveraging this adaptation to overcome, for example, increasing uncertainty in the system operation. As you see in the left, because of this learning process it will always be executed beforehand, right? We are not able to, for example, run it within a few seconds or within 5 minutes in order to put it into operation. It has to be trained, for example, day ahead. And given the increasing uncertainties, if without the normal operation, without this meta learning, we will train we have to handle a lot of scenarios. But with this meta learning, then we can train it into a sweet spot in terms of a meta state, and where we can quickly adapt to different actual conditions within, for example, intra-hour or 5 minutes ahead. And by doing so, we can significantly reduce the actual scenario we need to consider even in day-ahead training, and we leverage that day-ahead meta training for fast adaptation. So that's the basic idea of it. And more, when we developed this, we found this meta training and adaptations kind of procedure actually fit quite well into the existing operation time frame, because of our current operation is always divided into day-ahead and hour ahead and real time. So we can leverage this kind of operations time frame and fit our and our procedure quite fit into this distinction of different stage by leveraging this reducing uncertainty in terms of the actual system states, as you see in this figure on the second row from the top, that you can visualize it that there are reduced uncertainty through this process. So we can leverage that to adapt to the particular state through this time. This is how it actually works, and in this process that we were able to achieve very good adaptation. Next. And here is basically to show you, I have talked about many techniques so far. And starting here, I was starting to give you more concrete examples. And here's the load shedding one that for the emergence voltage control. And what it was trying to show is how we set this problem up. In reinforcement learning, as I talked about before, you will have observations, action, and the agents. These are and the reward. These are the key components in this problem setup. So in terms of observation, as you see for this particular IEEE 300 bus system, we use this for illustration, and because and also this system is open. And so this is so for this system we have about 154 buses voltage magnitude and 46 substations. We monitoring the load level. This is together combined as a continuous observation space. And the actions is we basically control these 46 substations, and each of these is load shedding is continuous between 0 and 20%, which means that it will be no load shedding or up to 20% shedding at each time step. And so the action space is 46 continuous. Next. And important part of reinforcement learning is the reward, because of a reward is how it guided the agent to learn and distinguish whether is a bad action or good actions. So the reward design here is basically follow these performance requirements, and while at the same time it penalizes these load settings and invalid action. If the action already, for example, if the load has been totally set for a particular substation, further setting will be penalized. So this is the basic idea that we incorporating the physics in terms of the performance requirement and penalize load setting. Next. And here I'm going to show you some results. First would be the IEEE 300 bus system that we published in the paper. Then next, my colleague Yusu would give you, for example, the demos in a larger scale system. And then, so this is the showing basically to show you the scalability of these parallel ARS algorithms. As you see, even up to more than thousands cores of CPU, it can still achieve very linearized scalabilities. And if we using the same amount of CPUs, we compare with another state-of-art IR algorithm called PPO, we are able to achieve these convergence in terms of this reward very much faster. And another point is it's more robust because of if you see the shade area, which is the basically the deviations if we using different random seeds. ARS was more robust regardless of the 5 different seeds we use, while PPO, as you see, the performance could have a very wide band, which means that it's quite sensitive to the choice of the random seed. Next. And here is about the deep matter reinforcement learning text results. And the key takeaway is first is the compare with the past. The extra adaptation just take 5 minutes for this particular case. And then this solution time in terms of 80 decision points is 0.7 seconds. So it can meet the real-time operation requirements. And we also compare with the MPC, which is supposed to give us a very good benchmark about the solution qualities in terms of how optimal this solution is. And as you can see in this plot at the bottom, above this voltage and the total load shedding, the solution is quite close to the MPC. And also by leveraging these methods adaptations, we able to achieve better control effect, in terms of controlled performance compared with the PARs without this method learning, as you see in this histogram. So the method makes it a more basically targeted to particular operation conditions, and this helps. Next. And here's about the once we embed this physics into this DRL we can further improve both the training efficiency and the control robustness. So, so the action masks that I talked about before were able to basically regulate these the neural network outputs such that we can filter out a lot of unfavorable actions at the very beginning. So you see, the starting point is much higher than we've done this mask, and we also achieve a higher, final rewards at the end. And from the table on the right, you see if we test it on very different new scenarios. So these are new scenarios 136, unseen in the training. We see it's the robustness of the solution is much better compared those without this mask. Even, for example, the row number 3 is the matter without RAS. This able to reduce this robustness, further improve the robustness by 75%. Next. So starting here, we will basically show you more interesting test cases and results. And here is the 2000 synthetic text system, which is the, I think will be very interesting for the industry folks, particularly if whether this will be able to, so try to answer the question, whether our solutions able to tackling something realistic scenario and realistic scaled up system. So in terms of the scenario, you see we basically handling a good mix of reflecting the current generation mix. I think it's a 2020 generation mix based on EIA data. And then we leveraging the NREL data set so that we can populate all the variabilities of these different generation outputs. So as you see around this 2 year, whole year, this outputs are quite varied based on this plot here. We are able to consider all these different operating conditions. Next. And a little more details about the training, because the scale of the system is so large, we definitely would like to leverage our understanding of the problem and to help improve the training. And one of the physics that we know in power system is voltage stability problem is more as a regional problem. So if we look at this system has 3 low hubs, low center hubs. So each of these basically is 1 metropolitan areas. And then we can leverage this decomposition for the first round trainings that we can decouple each of these actions. But at the same time, after this training, we notice that if the force is happening at the boundary, this isolated training may not be sufficient because of it may still require coordination among different regions. So we can, in the second stage, we can coordinate these 3 regions in terms of their control actions. So that's at the end how we use, like first is the divided training or distributed training, and then we coordinate their final actions in the second stage. And this helped us to first is to reduce the scale of the problem, and then improve these training efficiency. Next. So this is the data set for the training and testing. So it has 2 months, and then both these data sets are divided into test their, and totally different in order to test their, both is the generalization capability of these AI agents, that these agents not memorize this scenario, but it can find the patterns and properly extrapolate to some extent. Next. And this is the testing results showing that these we're able to reduce the load shedding if we compare with the existing rule-based under load settings control. We are not able to compare with MPC because the system is so large, we are not able to solve it properly. And the other thing is that even for such system, the decision-making time is, you see, is very similar to this IEEE 300 bus system, because of passing the neural network for making the decision is very time efficient. So it's very different from solving, for example, a differential equation. Next. So I think next I will pass this to Mariana and invite Mariana to give some more detail how we actually integrate this AI-based solution with VNR's tool and to basically complete the loop. And then Yusu will give a demonstration.
Okay.
Anna, please take away.
Yeah, thank you, Chenhua. Thank you, Marina. Before we switch, there's a question from the audience. Matthew London is asking you, how did you choose the 46 substations to observe and control? Chenhua, can you comment?
Yeah, good question. So in that particular case, I believe we're using this order substation rather than 50 megawatts. So it's more as that we focus on those larger substations, and because of those substations tend to be tend to be close to the actual load hub, and then have more capability to shut loads compared to those small substations. Yeah.
All right. Yeah, Matthew, if you are unhappy with the answer, give more comments and we will continue later on. Marina, please.
Thank you very much, and thank you, Chenhua. So in the first part of the presentation, Chenhua mentioned the word physics probably more than any other term, and mentioned convergence of physics, control, AI, and computing and simulation within the AI solution. But this solution has to be integrated with some computational engine and other parts of the analysis systems. So in my portion of the presentation, I'll actually focus mostly on physics, on the power system simulation, and on computing part of the overall framework. So I will describe now the setup for the Hudruck demonstration. So to validate and demonstrate the benefits of this approach and the advantages of Hudruck algorithm, we, VNR, together with PNL, set up a testing and simulation environment. Since we have been developing real-time controls in this project, we had to simulate a real-time analysis framework. And we collectively decided that the best foundation for this would be a linear state estimation as that uses synchrophasor data as one of its main inputs. And in turn, the LEC output was used as a situational awareness tool, since we're talking about improved operator performance and control, etc., as well as the input to the control module that Chenhua discussed. I think next one, please. Okay, so let's shift our focus for the next few minutes to the simulation environment and state estimation. We all know that state estimator is the backbone of every utility's operational environment. And it is designed to produce a system state based on the best estimates of the state variables, usually voltage, magnitude, and phase angles. And the core calculation in any state estimator or in many state estimators is minimizing the sum of the difference, the sum of the squares of the differences between the estimated and the measured values of variables. Next one. Why linear state estimator? Again, there are we can classify state estimators into three categories: conventional scalar-based non-linear, linear based on synchrophasor measurements, and hybrid that uses both inputs. So one of the key reasons we have chosen linear state estimator because of the high speed of state estimation, and we wanted to demonstrate the effectiveness of the controls that we developed during the project in real-time environment. So usually the speed of linear state estimation is around 30 times per second for transmission and frequently 60 times per second for distribution system for a 60 Hertz system. The speed usually, the high speed is usually to using a direct solution, non-iterative solution. Since we were simulating a control room environment in the demonstration phase of the project, we wanted to be as close as possible to that environment. And there are two more reasons of using LSC, as it improves the real-time reliability, because it serves as a quality check for conventional state estimator. And like in any utility, we would have multiple tools for power flow or contingency analysis or even voltage stability or transient. We can verify the results if we're not sure or results are suspicious. But every utility has only one state estimator, and we make all our decisions based on only this one tool. We trust that it's very accurate, but it's always good to have a check. So LSC can serve as a check, and also LSC improves the resilience, which is another buzzword right now in the industry, resilience of real-time operation, because there are frequently situations when conventional SCADA-based state estimator fails to solve for different reasons. And in this case, LSC serves as a backup for conventional state estimator. So that's why we decided to use LSC as the backbone of our demonstration, hazard demonstration. Next slide, please. Okay. Thank you. So the hazard algorithm was integrated with Windar Energy's PMU rows, which includes multiple capabilities, linear state estimator, and linear state estimator includes, like any state estimator, but data detection and conditioning if possible, observability analysis, which is more important in LSC than in conventional SE, since we have less PMU measurements than SCADA points, weighted least squares method, conditioning and expanding PMU output streams, APIs, visualization, and also creation of PMU-based cases, similar to how we create SCADA-based SE cases, and then using them for further advanced applications. So for the next slide, please. For the demonstration, we integrated PMU rows with PNL's grid pack, and as the input, we were receiving state estimator cases from grid pack to, since we need network parameters, topology, connectivity that comes from the model. Also PMU data in IEEE standard C37118. And these are two major inputs, I would say. PMU is the major, second most important is the model. And then of course, the mapping between the model and PMU so that we know where the measurements are originating from, and supplemental data for various scenarios and events that Yusuf will describe in more detail in the concluding portion of our presentation. The output is very important. It's again integrated with the grid tag, and the main output is the estimated or processed and expanded PMU stream. So it includes not only estimated or processed values of voltage vector and current vector at locations where PMUs are installed, but also at locations where PMUs are not installed but are observable, can be calculated based on observability analysis, Kirchhoff law, Ohm's law, etc. And that way we have a more complete visualization and also observability and analysis of the network. And there are other supplemental outputs which I don't think are important for our presentation today. So we'll move to the next slide, please. Okay. So GridPath simulated PMU data which includes noise, bad data, which is really important to make our simulation more realistic, because in real time or in real life, we never see pure PMU data. It always comes with noise, dropouts, and delays and other issues. So GridPath simulated the imperfect PMU data at 10 frames per second, 10 measurements per second, and that was sent to Windar's PMU ROSE LSC. Next one, please. And we then utilize a multi-step process similar to any state estimator. It can be simplified here. It includes many more steps, but they can be categorized in identifying bad data, and then it can be either conditioned or removed, and then filtering and smoothing. And we use exponential filter for this particular implementation, weighted least squares method. And after we removed bad data and also filtered it, we could perform event detection, because that's what we wanted to see. Whenever a fault occurs in the system, we would have an alarm, and then the control algorithm can be initiated to identify the optimal control actions for that particular event. And we also visualized the event and bad data for the operator. Next one, please. And this is a display of the visualization when the fault starts. So we see an alarm, and we also see on the right on the chart the PMU data and then estimated data after LSC, and then we have notification when a bus fault event occurs in Pacific Core system. So this is the WCC system, Huang, types based on the 300 bus system and then 2000 bus simulated Texas system. So these simulations were performed, and the demonstration was performed on the actual WCC system with faults and scenarios provided by our host utility, Pacific Core. So the bus fault event is identified by LSC, and this information is sent to the control algorithm, and Yusu will pick up, starting with the next slide, and will explain more about the case study for the Pacific Core and how the output from the LSC is incorporated into further Hadrock framework. Thank you. Yes, sir?
Thank you.
Hi, thank you, Mariana, and thank you, Chuhua. Can you hear me?
Yeah, I can hear you.
Okay. So this is actually the GUI, a screenshot of our GUI to show the Hadrock performance on the particular Pacific Core system. I will show you a video in my next slides, but let's give you some of the basic information of this GUI. So for the left part, it will be the topology for the system. And then in the middle, the top one is the actual generated local angle curve by our Hadrock algorithm. And the one in the middle is the curve if we used today's out-of-step protection algorithm. And the last one is basically if no action taken, just what will the system be? So apparently it will become unstable. And then for the right side, it will be the more information about actual action messages, including the time and which generators are tripped, and with their generator capacity. And also at the bottom of the message will be the system fault information, including what kind of tripping or events at what time. So in particular, for this particular event and the hydraulic algorithm, for this condition, we tripped only one generator, about 300 megawatts, by tripped at about 3.1 seconds. You can see the right corner here, 3.1 seconds. If you use the auto step actions, they will require 8 generator trippage to bring the system back. And the total amount of generator capacity tripped is about 1 gigawatt here. So we can see that it's about 20% improvement in terms of the responding time. It's about 70% improvement in the trips generator output. And as Mariana mentioned, so this algorithm, I think the one unique feature of our project is we actually work with Vaiman Energy to integrate our algorithm with their commercial tool. So next, I'm going to play one video, basically the GUI we developed to see what's actually working. So this the lotto angle curve. We see, and then this event identified here, and right corner shows the event as 9 trip event. And then the action will take work. And the first one, the top curve shows that our hydraulic actions tripped 1 generators at 3.1 seconds, and with a total amount of 300 megawatts. The auto step control actions result in about 8 generators tripped at 3.7 and 3.8 seconds. The total generation amounts about 1 gigawatt. So this is basically a quick impression about how the algorithm works and how its performance compared against other existing control actions. There's a demo part. If there's no other questions, I'm going to go to the next slide. So this is, by the way, all the algorithms are open source now. You can find our hydraulic AI algorithm training source code at GitHub. This project heavily leverages the GUI-PAC simulator, which is a high-performance coach for power system application libraries. So you can identify the GUI-PAC, and we have the Python wrapper developed for the OpenAI Gym interface, which is also part of the GUI-PAC in the Python branch. So you can you can go to this website to download this code and the code to have a test.
Yosen,
Go ahead.
I do have a question. Is implementation the one that Qiuhua was talking about on the reinforcement learning, like the meta version? Is this for reinforcement learning?
Oh, you mean the hydraulic? Yeah. Yes, it's
Yeah.
yes.
So when you are using the PMU to do reinforcement learning here, let's say sometimes there's a PMU that failed the communication, but you are still training the neural network. So how do you do that when the observability is changing slightly due to communication failure?
So Qiuhua, could you please help here? I know we heavily leverage the LSE.
Yes. So I think so. Yang, thank you for your question. I think this is very important. So I think this is related to how we, in one of the slides you see in our architect, we have both the learning module and another one is the execution module. So in the learning module, we are primarily using the simulators. So in that regard, it's not directly using PMU output from this LSE. So it's using the PMU. We assume that we have PMU in the system for some of those substations. We're using those as input for this PMU-based voltage stability control. Why when we are in execution mode, and this is the power of VNR's tools come in, where their tool can handle both the, for example, those data quality. and then extended the coverage of PMU as well, because the LSE capabilities can be extend some of the unobserved nodes, and once it goes through those LSE. So these are how it actually, partially handles some of those, PMU unobservability issue. And another thing is we do test in a few scenarios, we test the port. For example, we lost those input signals, and as well as it has been deteriorated by, for example, a large, above a normal noise conditions in our algorithms. It has been, at least for those test cases we have done in our paper, it worked quite well. Yeah.
Okay. Is it okay to quickly add?
Yeah, go ahead, Mariana.
Thank you. And this and I'll just second what Chuhua just mentioned. That was one of the main reasons of using LSC versus the PMU data stream, because there are various issues. You can lose communication, you can have delays, you can have you can have outliers. There are multiple issues, and I will not go into the details of that could happen with the PMU stream and PMU data quality. And that's why, let's say, we don't run any advanced applications currently in the control room based on SCADA data. We run state estimation first, and then we take the output of the state estimator and use it for any analysis or control applications. So the same idea was here, to remove the bad data, to condition the bad data, and then use that as the input for control algorithms, not to skew the results up. And the second, I think, aspect that Chuhua also touched upon is also very important, is the expanded observability, because we try to simulate the more or less current state of things where in the industry where you would not have a PMU like SCADA point at every location. So we had several hundred PMUs for the WAG system or for the Pacific Core system, and they provided much more extensive coverage due to the expanded observability analysis that LSC performs. So we had, let's say, 400 signals as the input, but we had 1,200 plus signals as the output. Out of those 1,200, and these are not the exact numbers, this is just the magnitude of the numbers that we've seen signals. So out of that 1,200 signals, some of them were PMU signals, were initial 400 signals minus the data that was bad that we could not fix and could remove. Some of that was processed data, estimated data, improved data with bad data conditioning methods, and some of that was calculated data based on observability analysis. And that cleaned and processed and expanded PMU stream was then sent to the control module.
All right. Yeah, that's very comprehensive. Thank you, Mariana. Yeah, you cleared my doubt. Thank you.
Okay. So let me move forward. So, I will take this opportunity to talk about some recent progress in AI for grid operations. So first of all, I will cover a few of our PNN era, projects, and then I will transit to Chuhua for the rest of the presentation. So before I move forward, I want to talk about AI machine learning capability, in particular in data side PNN era. So we do have a BOE PMU big data analytics 4R. We have a normalized and dedicated cloud environment for about 30 terabytes data, including 600 billion records. We have a full-blown PMU network that could be more than 1 petabytes a year data size. We also have a EIOC, which is a electrical infrastructure operating center in our lab for the demonstration purpose, which can be used as a backup control center, by the way. So we have a dedicated reliability grade string data storage and curation, and we are approaching petabyte capacity to support our research and industry cooperation, particularly with the utility like CAISO and BPA, and some of the Eastern utility as well. And we do have API data repositories, including real and synthetic data sets. And we also support the LARM program, which is the North American Electricity Reliability Modeling, Resilience Modeling program. And so we do have a bunch of real data in our lab. And then with this data, we are able to do some projects related to AI machine learning. I will talk about 4 projects only for this one. But in our lab, we have, I think, more than 20, maybe a lot of AI machine learning related projects. So the first one will be the LAG. So it's a learning to adaptive control complex power system network. So basically, we are able to reduce the overshoot magnitude during fault by more than 10 times. So this is or maybe the next slide is talking about more details. So, but the second one is Mango, which is a mode analysis for grid operation. So we are adjusting real-time operating conditions for damping improvements using AI machine learning approach. Then the third one is Trust, which is a transformative ROS tool. We adjust the ROS tool parameters using AI machine learning tools to significantly speed up the ROS study procedure. And then we have a Hippo, which is a high performance power system optimization tool. We're able to achieve about 35 times faster optimal solutions for billions of energy savings. This project was working with MISO. Just got the patent approved last week. So this is some more details of these 4 projects. So the top corner one, the left corner, upper corner one is the LAG, learning to adapt and control complex power grids network. So it's AI-based online controller parameter application adaptations. So the use case is a double phase inductor generator with DFIG for the wind farm for right-through cases. So with our AI algorithms, as well as we call the ADRC stand for the active disturbance and resistance control. So with a control algorithm and AI machine learning algorithm, we are able to adjust the control parameters in real time, so we can significantly reduce overshoots during the fault is by more than 10 times. And then the right upper corner is Mango. So again, by using AI machine learning techniques, we are able to provide actions that help improve the damping conditions by adjusting the operating conditions. So let's consider the difference with Mango and without Mango. And then the left bottom corner is Trust. This is leveraging the HPC cloud computing as well as the AI machine learning. We study large scenarios for the Pacific Coast system as well. So with our tool, we are able to significantly speed up their study time from, well, basically reduce their study time from months to minutes. So that's a big jump, a big improvement for their ROS study implementation and planning as well. And then the bottom right is Hippo. So this one is we use AI to accelerate the solving power market cleaning problems by finding the solutions or initial points earlier. And then we also leverage the SFT, which is simultaneously feasibility testing HPC technology to help us to quickly identify the solutions. So these are the 4 projects in our lab. We do have other more ongoing projects, including like dynamic security assessments, contingent ranking, and a model conversion from operating to planning. So a lot of other projects ongoing. So if you are interested, please contact me. We can have offline discussions. So I'm going to transfer to Qiuhua if there are no questions.
Right, thank you.
Yes, so here basically I want to talk more about the progress in terms of the edge of the system because of the DER proliferations and rapid developments of EVs, all that require, we are not just deploying AI at the control centers, we're also deploying AI at the edge of the system. So this is showing some recent progress like partnering with NVIDIA and others that developed this smart grid chip basically to provide this computing capability at the edge for sensing, computing, and AI learning and influencing. On top of that, we also develop open source software ecosystems by leveraging these existing packages developed by NVIDIA, but also to develop particular applications for the grid operations, ranging from anomaly detections to DI communication, control, and management. So I just want to show these are happening right now that from both the hardware and software for empowering the edge intelligence. Next. And here's a quick summary. I want to skip this because of the time interest, so I will probably let's pass it to the perspective.
Okay.
Okay. This perspective, I think, is a continuation of the discussion that we are basically transitioning from centralized control and centralized AI applications to distributed control and distributed AI. But there are gaps in terms of how we can coordinate them because of now these are two kind of communities. We have been, one community is focused on transmission, one community focused on distribution, but they are one grid. So how to coordinate both sides is one open, very wide open space. And another thing is because of the 4-order 2x4, I think there are many opportunities and great values as well by coordinating both the centralized and distributed control. And I think here, the last thing I want to highlight is about for the edge, concerns of the data privacy and security from our customers is we should respect them. And at the same time, for example, AI's development like the federal learning could potentially address some of those concerns. And we could leverage that to make our control and management more resilient to those data privacy and securities. Next. And last thing I want to just recap that the frame of this talk is convergence of physics, AI, computing, and control. This project showed promising results, and there are definitely many other areas that we could touch on and apply to on both centralized and distributed applications. So we would love to hear your perspective and as well as your potential application of such kind of ideas and even our platforms. So we make it open source. So we would love to hear more and in the future that you make something different by leveraging this tool. Thank you.
Okay, thank you, Qiuhua, and thank you.